Hello. Today we are going to be taking a look at an alternative method for finding absolute extrema, something that we call LaGrange multipliers. This week we talked about how to find absolute extrema. Remember, we're talking about maximums and minimums. It was a very complex method. For example, if we wanted to find the absolute maximum of our function y f of x y equals 3x minus x squared y plus y squared, and we're bounded by the circle with a radius 16, we first had to find all the relative extrema, that's our gradient, set those equal to 0, find all the extrema on the edges, and then all the extrema on the endpoints. They took a very long time to solve. They weren't very fun for us. Well, enter LaGrange. LaGrange we mentioned last year when we talked about Lagrange error bound, and that was a method we used in series and sequences in order to estimate the error in an approximation. At the age of 19, the age of some of you guys going to college, Lagrange came up with another method for solving for these absolute extrema that will not take as long. So an example, let's say we want to an example to show you how this works is, let's say we want to maximize the area of a rectangle inscribed in an ellipse with a major axis of 8 and a minor axis of 6. So let's say I have an ellipse here. It has a major axis of 8, 1, 2, 3, 4, 1, 2, 3, 4. And a minor axis of 6, so 1, 2, 3, 1, 2, 3. So there's my ellipse. And inside this ellipse, I have a rectangle. Now, our mission is to maximize the area of this rectangle inscribed in this ellipse. Now, I can get the length of my rectangle, that's not going to be too bad, as being 2 times y. And the base of my rectangle is going to be 2x. So, from geometry, I can now get the area of my rectangle. Remember, it's going to be 2y because this is a y value and that's a y value, so we just double it. From geometry, I can get the area of my rectangle as being 4 times xy. So therefore, I can write this area as a function. A of xy equals 4x times y. Now, you might recall, this is a rational function. Therefore, this is a hyperbola. Right there. So, if I were to draw my ellipse, again, there's my ellipse. And if I were to draw my hyperbola, now, I don't know the exact part of the hyperbola, but the hyperbola, if I were to graph this, I could say like y is equal to a of xy over 4x. The fact that we're just over x, so that this hyperbola could look something like this. Now, the only problem is, depending on what the area is, this hyperbola could take on all sorts of values. There's my hyperbola. There's my hyperbola. There's my hyperbola. I'm going to try to make it touch there on purpose, okay? What we want is where the hyperbola touches. We want to find the hyperbola that touches our ellipse. So we want to, you might recall, these are sometimes what we call level curves. So what we want is the level curve that touches our ellipse. That meets our function. In this case, our ellipse. And that's what we're going to be trying to find today. In other words, if we use the area as the dependent variable, we can say that all level curves represent all possible areas of the rectangle. So that's what this says. That this function, that this hyperbolas here represent all the possible areas. So all possible areas. If the function represents the equation of the ellipse, it becomes the restriction we want to use. So in other words, what we're saying here is that the level curves of our function, a of xy, represent all possible solutions. What we want to find is the level curve tangent to the ellipse. That is our solution. So let's look geometrically at what we're talking about. If I draw a bunch of level curves here, hyperbolas, right here. If I draw a bunch of level curves, those are my level curves. The level curve that touches the ellipse, there we go, there it touches. The level curve that touches to ellipse, this point represents the solution to our optimization problem. Now, why does that work? Well, if we think about in terms of direction, perpendicular direction. If I'm perpendicular to my level curve, we can be heading in all directions. However, at the point where they're tangent, the level curve, the direction of my circle or my ellipse will be the same as the direction of my level curve. And that's what this says right here. Where the curves are tangent, they have the same direction. Now, let's think about in terms of the calculus. Well, what finds the quickest way off a level curve? We talked about this. If I have some level curve, the fastest way off of it is going to be perpendicular. We call that the gradient. So where the level curves are tangent, they have the same direction. In other words, they have the same gradient. And that is what we're going to use to solve our optimization problems. What is the relationship between the gradient of the level curve and the ellipse? Well, if they are parallel, we can say the following: that the gradient of the function is equal to some multiplier times the gradient of what we call our constraints. We're going to talk about that in just a few moments. This right here is a multiplier. Who came up with this multiplier? Well, LaGrange. So this is going to be the function that we are trying to maximize. This is the constraint. What's constraining us? In this case right here, the function would be our function up here. G of x would be our circle. Now, the multiplier is the Greek letter called lambda. We call it the LaGrange multiplier. So let's take a look at Lagrange's theorem, what it means, the results. So all this kind of says the same thing right up here, that we can solve for a maximum minimum by using this formula right here, which we got up here. Lambda, that is the multiplier, ensures made a mistake there, can't talk and write at the same time, is the multiplier. This ensures that the two curves are parallel, that they head in the same direction, that their gradients head in the same direction. And that's what we're looking to find here. So how does LaGrange work? In order to solve this, in order to use this equation, we have to solve a system of equations. Now be very careful. G of xy would only equal c. So to find the maximum or minimum, this is what we're going to have to solve. Ready? We're going to take a look at the value of the gradient in terms of x, the value of the gradients in terms of y, set those equal to each other, and we're going to look at the constraint itself. This last one is just our constraint. Right here. So notice, we're going to take the gradient with respect to x, set equal to the, of our function, set equal to the gradient of our function, the partial with respect to x in our constraint, and we do the same thing for y's. And we're going to solve the system. Now, why do we need 3? Well, we're going to have 3 variables. We will have 3 variables that we have to solve. Okay? The first one, we have to solve for x, y, and lambda in most cases. Okay? So remember this. This is just quickly, just review. These are a list of partial derivatives. So let's take a look at some examples. So go to video 2, and we'll go take a look at some examples. I'll see you then.